Hi, my name is Cooper Stone, and this is my Physics 2212 Lab 3 about the magnetic field of a bar magnet. The purpose of this lab is to use the PHYS law to determine distance dependence of the strength of a magnetic field of a permanent bar magnet, and then comparing this magnitude determined experimentally and computationally. Here we assumed a couple of things, such as the accuracy of the equations, the magnetometer, and the dipole nature of the bar magnet. And the main results found that the dipole moment was 2.358 nanometers per Tesla, and the experimental and computational net magnetic field differed as seen below. So some essential concepts. One main one is the Biot-Savart law, both perpendicular to the axis and parallel or on axis. As you can see, when perpendicular to the axis of the magnet, it's half as strong as parallel or in line with the axis if the distance is the same. And these equations were used with experimental data, but for the computational data, these equations were used to determine things such as n, the distance dependence of strength of magnetic field, and then the more advanced version of the Biot-Savart law, which works better for larger distances. So for the experimental procedure, a variety of tests were performed to find the location of the magnetometer in my phone, and then once that was found, I used that to determine strength of magnetic field at certain distances and also on axis, and also the strength and distance of the magnetic field off axis, so diagonal to the axis of the bar magnet. And then for the computational model, I just visualized that data and used the equation here at the bottom. I used that equation for the computational model and then compared the two net magnetic field magnitudes that I found. So you can kind of see a simple representation of the system. In this case, this was after I found all the on-axis measurements and wanted to find the diagonal measurement of the magnetic field. And gravity and normal force are both acting here, but they cancel one another out, supporting both the phone and the magnet. Here's my experimental data for the first part of the experimental procedure, where I measured on-axis strengths. And as you can see here, based on that data, I was able to graph the equation y equals negative 3.1008x minus 14.567. And that means that the value of n is negative 3.1, which is about approximately negative 3. And that agrees with the Biot-Savart law, which states that distance dependence is over r cubed. And then I also found the value of k by taking the natural log. I found k to be equal to 4.717 times 10 to the negative 7th power. And here, using those values and the equation for magnetic field equals kr raised to the n and the normal Biot-Savart on-axis equation, I set them equal one another, plugged in the values for the dipole moment and for plugged in values for k and the other constants, and I found that the magnetic dipole moment was 2.358 nanometers per Tesla. And then for the rest of the experimental procedure, this was for the diagonal component, and I used the measurement of Earth's magnetic field to correct it, and found that diagonally the magnitude of the magnetic field was 5.55 times 10 to the negative 5. Here's some of my glow script code. You can see me setting the constants, defining the function, and creating arrows to represent the objects and magnetic field. And then I created more arrows here as well to represent the magnetic field. And also, as you can see on the right, I determined the magnitude of the magnetic field according to the newer equation and printed it. And this was the result of that. The blue arrow is representing the magnetic field perpendicular to the axis, the orange arrow is on axis. Notice the difference in magnitude, and then the magenta arrow representing the magnetic field diagonal to the bar magnet. And as you can see there, the computational model found the magnetic field to be 2.211 times 10 to the negative 5 Tesla. So it was expected that n would have a value of approximately 3, and my results agreed with this, but there was a discrepancy between the computational and experimental magnitude of magnetic field, and this could be due to a variety of reasons. One main one is that the equation used in the computational model is known to not be as accurate when close to the bar magnet, so that's one. Inaccuracy of the magnetometer or other magnetic things that would interfere with those readings could have altered the data, causing a larger reading. And then also just not correctly accounting for Earth's magnetic field. It was observed that the magnetometer was far away. It is near zero because it's too far for it to have an effect and decreases exponentially. It was found that it was false for the second and third statements, as moving it changes the net magnetic field, and moving it farther decreases it. And then the last statement was true, which is that as you move it closer, the x component of the field increases. What if I hadn't oriented my experiment for magnetic north? It would be inaccurate, as I would take an Earth's magnetic field as well. And then if I stuck two identical magnets together, it would increase the magnitude of the field because they would be supporting one another.